moving. Just wait a second. It's not letting me. There we go. Hang on. Okay. Can you see my slides now, Niranjan?
Yes.
Okay. Thank you. So, as Niranjan said, I'm going to talk to you today about carbon dioxide capture. I'm going to cover 5 or 6 different topics. I'll firstly give you a brief introduction to my university so you know where I'm coming from. I'll talk a little bit about how carbon capture and storage fits into the climate change picture. I'll then talk a little bit about the work, the research I do on gas separation membranes, then the research I do on membrane contactors, and then how we scale that up into pilot plant trials. If there is time, we'll also then talk about CO2 capture and utilisation in microalgae. So let me start by letting you know where I come from. So I come from Australia, which you can see there in the graph on the left-hand side. I don't know whether you can see my pointer there, but we're in Australia here, and of course you guys are sitting there in India, so relatively similar parts of the world. Within Australia, I live in Victoria, which is at the bottom part of Australia, and in the city of Melbourne, which is right at the bottom there. So we get less hot weather than perhaps other parts of Australia. It is a wonderful city though, Australia, and Melbourne. I invite you to come and visit us there one day. So it's a city quite small by Indian standards of about 4.5 million people. It's consistently ranked as one of the world's most livable cities. For many years, we were actually ranked as the most livable city in the world, but we've recently been taken off the top of the list, and we're now second to Vienna, but still a very good place to visit. We're ranked by the QS rankings as the 3rd most student-friendly city in the world. So again, a good reason for you guys to visit. Very multicultural, hundreds of different nationalities represented within the city. And of course, you know that we're Australia's sporting and cultural capital. Some of you may have watched the Australian Open recently, the tennis, but of course, I'm sure you all had your eyes on the MCG in Melbourne over Christmas, over the Christmas period, where of course the Indians beat us, much to our disgust, but your joy, no doubt, in the cricket, in the Test series. So very well done to all the Indian cricket fans in the audience. We're very lucky that the University of Melbourne sits very close to the centre of the city. So this is our campus here, and you can see the city buildings in the back here. So we are very lucky to live very close to the middle of the city. We're ranked the number 1 university in Australia, number 31 in the world, and number 7 in graduate employability worldwide. So we're pretty proud of our university's rankings. And as Niranjan mentioned, I'm head of the School of Biomedical Engineering and Chemical Engineering. Most of you should know what chemical engineering is because I'm here, you're studying those subjects. But biomedical engineering is quite a bit different. It's looking at healthcare problems and tends to be focused on research relevant to medicine or hospitals. So that can range from implants to replace your hip or your knee, through to deep brain stimulation as a treatment for epilepsy. But let me move on to the topic of my presentation, which is carbon capture and storage. And I feel it's always important to start these presentations by making sure that we're on the right page and that we do understand that global warming is happening. And this is my favourite graph that, to me, best illustrates this phenomenon. So I'm plotting on the left here the parts per million of carbon dioxide in the atmosphere. And the x-axis here is time, but you'll see it's very long periods of time. This x-axis here represents 400,000 years, 4,000 centuries. So you can see a very, very long time on this planet. And you can see over those 400,000 years that the CO2 concentration in the atmosphere has never exceeded 300 parts per million. These dips here, or these cycles, represent the successive ice ages. So you can see this last ice age here finishing about 10,000 years before humanity before today's date, if you like. All of humanity has only ever existed beyond that last ice age. So this is the period representing the period of humanity. And you can see that we've had a very devastating impact on the environment, with that CO2 concentration crossing the 300 ppm line around 1950 and continuing to escalate. I prepared this graph 2 or 3 years ago, and even what I've marked there as the current level is not true of today. So if you were to look up the most recent statistics on the web for today, that's not going to show me the, oh, there it is there. We're now here at 410 parts per million in the atmosphere. These changes are already having significant impact. You can see the increase in global sea level rise, global temperature rise, and the decline in the amount of ice in both the Arctic and the Antarctic. And it's anticipated that even if we were to stop putting CO2 into the atmosphere tomorrow, these changes will continue to play out for centuries because of the amount of CO2 that we've already put into the atmosphere. So we obviously need to address this issue, and there are many ways we will do that. I'm sure you've heard about the huge increases in solar energy and wind energy and the projects going in internationally in that space. But carbon capture, utilisation and storage will also be part of the response, and they have to be. Even if we were to move totally to solar and wind as our sources of energy, we would still be producing carbon dioxide, for instance, in the production of cement or in the production of oil, of iron and steel. So carbon capture, utilisation and storage must remain part of that response. And I won't read out all the quotations on the page there, but you'll see that the United Kingdom also sees climate change as being, carbon capture and storage as being an important requirement in their own response to climate change, as does the International Energy Agency and indeed the Intergovernmental Panel on Climate Change. Carbon capture and storage projects are starting to emerge internationally, and you can see on the picture of the globe there a number of the projects that are currently underway. Let me profile some of those. So we have Boundary Dam in Canada. This is a large project shown here in construction, but has been operating over the last few years. And that has put in at least 1 million tonnes of CO2 underground for use in enhanced oil recovery. We have Petronova in the United States, where 3.8 million tonnes of CO2 were stored underground. This was quite a large project, but it is one that's on hold at the moment. You could potentially argue that's because Trump has been in charge, but who knows? In Japan, we have the Tomokamai Project, which has been producing capturing CO2 produced from hydrogen production in an oil refinery, and that's injecting about 100,000 tonnes per year of CO2 underground. In Abu Dhabi, there's a significant carbon capture and storage facility capturing CO2 from direct reduced iron, and that's injecting about 800,000 tonnes of CO2 per year, with a second plant now being planned. And finally, in Australia, we have Gorgon. Gorgon is a large project off the northwest shelf of Australia, where CO2 is produced alongside natural gas when we explore, or when we're producing natural gas from underground. That carbon dioxide is captured and currently being injected off the coast. So there's 3 million tonnes of CO2 that's been injected so far in that project. I'm going to, though, move on, and I'll talk in a minute. I'll pause in a second for questions, Kriti. I'll just finish with this slide. But the research I'm going to talk to you about that I do in this area goes across all scales of development. So I look at the molecular scale at producing better membranes to capture carbon dioxide that have more affinity for carbon dioxide. We test these membranes on a laboratory scale. So this is a picture of one of my original PhD students showing one of the membranes we've prepared in the laboratory and that we test within the laboratory. We've then taken those membranes out to pilot scale and a number of pilot scale facilities. And while we haven't yet been involved in demonstration projects within the country, we've certainly done simulations of what makes the economic best project for these situations. But before I go on, I'm just going to pause and see if Pretty can let me know whether any of you have had questions that you want to ask me.
Yes, Professor. Actually, I had a question myself. That is, you mentioned the number of projects that are going on in the different countries. So how long does it typically take to build a facility for a particular country? For instance, the one you mentioned in Australia?
It is quite a long process, so it depends where you start, if you like. From the first initial planning up until operation is usually of the order of 5 years. But that might be a couple of years of desktop studies and essentially getting the funding together from the various agencies that you would need to get it from, and going through the environmental approvals, and then it would be another year in a more detailed design, and then 2 years of construction. So you do need quite a period of time, and this is important in understanding in our response to climate change how rapid we need to respond, because these things do take time to build.
Okay, thank you. So I think we can continue. We do not have any further questions right now.
Okay, no, that's fine. So I'm going to talk to you about gas separation membranes, which is probably the technology I spend most of my time on. And because I'm not certain of my audience, I'll start from the very basics of how a membrane like this might work. So in a membrane, a membrane is essentially a filter operating at the molecular scale. So we have a mixture of gases passing across the membrane, and the more permeable gas penetrates through the membrane and is collected. So in most of our operations, we're looking for a membrane that is selective towards carbon dioxide and less selective for other gases, typically nitrogen. This is a cross-sectional SEM image of a traditional flat sheet membrane. This is actually a water treatment membrane, but it's one I have a particularly good image of, and it's very similar to the gas treatment membranes that you would see. So the bulk of the membrane is actually just there for mechanical support. We have this layer here, which is a non-woven polyester fabric. On top of that is an interlayer that reduces the pore size more to what we need for gas separation. But even this layer here, you can see the pores are still too large to actually discriminate between carbon dioxide and nitrogen, or in this case, water and salt. So this layer here is made from polysulfone, but in a traditional gas separation membrane, this would be cellulose acetate. The actual separation takes place in the very thin skin layer on the surface of this membrane. And there's a lot of technology involved in getting this layer present there as a very thin layer, as well as in tuning the properties of that layer. But some of the research we've been doing is looking at making a membrane layer that is more selective towards carbon dioxide. So you can see in this case, we're using a grafting technique where we actually attach to the support layer, which in this case is polydimethylsiloxane, these cross-linked polymer chains that have a very strong affinity for carbon dioxide. And it's actually this ether linkage here that is known to have very high affinity for carbon dioxide. So we can coat a very, very thin layer on top of the polymer that gives us good selectivity for carbon dioxide. You can see that in the results shown here. So you can see here the selectivity of the membrane of CO2 over nitrogen versus the flow through the membrane, which we refer to as the permeance. And you can see that the membranes in this case make it into what we see as the target area. That is a selectivity of at least 10, but preferably 20 to 30, and a permeance of above 1,000 gas processing units. So that's some of the four fundamental work we do in building a better active layer or surface layer. More recently, I've also been interested though in building a better support layer, because that support structure that I showed you does add some resistance to flow, particularly as we get the properties of the active layer right. So we've been looking at a process known as electrospinning for this purpose. In this case, we take a polymer solution, we pass it through a needle, but in that needle we have a high voltage applied, and this generates a very fine thread of polymer that can be collected. This is a technology not developed by ourselves, but one that's been around for the last 10 or 20 years, and it produces this type of support. You can see that the porosity of this support is much, much higher than that of the polysulfide layer that I showed you before. So this offers much less resistance to flow through the membrane. However, it can be lacking in mechanical strength. So one of the things we've been doing more recently, and this is an invention that we have recently patented, is to take that thread and to apply it onto a rotating drum. That generates these nanofibers or these threads to be aligned with each other. We can then rotate the support, if you like, and apply those threads in the opposite direction. And the net effect is we can produce a cross-hatched support that has much greater mechanical strength and actually slightly higher porosity than the more random structure you see on the left. So you can see here some of our aligned nanofibers and an image of what it might look in a cross-linked form, although it's difficult to get the image of the actual final structure here. So this isn't quite what the final thing would look like, but it certainly gives you an indication of what we're trying to do. So I do work in this sort of fundamental membrane development, but I'm also probably much or more so interested in how these membranes perform in the real world. Because what you do in the laboratory is often nothing like what actually happens in the real world. To give you an indication, I've referred to this gas separation process as being the separation of carbon dioxide from nitrogen. But in reality, there are many, many more components within the flue gas. So if you're looking at a classical post-combustion flue gas or a biogas, you could be looking at the flue gas from a cement factory, a steel factory, from hydrogen production, or that natural gas sweetening operation that I showed you taking place on the northwest shelf of Australia. In virtually all these cases, the gas stream will contain water vapour, and this is a particularly nasty additive to have in the gas stream. But you'll also have other hydrocarbons. You'll have BTEX, which is the word for benzene, toluene, ethylbenzene and xylene, which are particularly nasty aromatic hydrocarbons that can be present, as well as all these other components. And all of these components mean that the membrane never performs in the real world in the same way as the laboratory. And this has been an area where I've spent quite a lot of time doing research. As an example, this shows you the effect of water vapour that we've observed in different membranes. So cellulose triacetate, as I mentioned, is the membrane that's mainly used in natural gas processing. And you can see here, if I'm plotting the permeability versus the water vapour activity or the relative humidity, the amount of water in the gas, you can see that in this membrane, we actually see a loss of permeability out to about 50% relative humidity. And this is because the water vapour competes for space in the membrane with the carbon dioxide. But then after a certain point, we actually see this permeability going up again. And this is because the water vapour starts to actually swell the structure and to open it up. So we see quite different behaviour. This is another membrane used in natural gas sweetening, and we again see interesting behaviour. In a dry gas, we see what you would know as Arrhenius behaviour. I'm sure you've all studied the Arrhenius relationship in your chemistry classes. So if we plot permeability versus 1 over the temperature, where the permeability is on a log scale, we see a nice straight line when we have pure CO2. But you can see that once we add water vapour, 20, 40 or 60% relative humidity, we see this very odd behaviour. We see the permeability increasing with temperature up to about 70 or 80 degrees C, and then decreasing with temperature again. And this has to do again with the ways the water interacts with the polymer. You can see other graphs here. So you can see matrimid another membrane used in natural gas sweetening, and you can see that permeability falling with temperature. This is the same graph for showing Matrimid, but there's a lot of interest in the literature, and maybe you've had some presentations on what we refer to as mixed matrix membranes, where you put additives into the polymer to increase the permeability. That works well, very well, if you have a dry CO2 nitrogen mixture. But you can see that when we have water vapour present, only some of those additives are effective in improving the performance relative to Matrimid. Most are ineffective and actually cause a reduction in permeability. So a lot of what is published in the literature simply won't work in the real world once there's water vapour present. So that's what I wanted to talk about on gas separation membranes. Again, I'll just pause there and ask Kriti if there are any other questions on that topic.
Yes, Professor, there actually are. So the first question that we have is, can we use these membranes in automotive catalytic converter to capture CO2?
You could, but no. A membrane, gas separation membrane requires a pressure drop. It requires a pressure driving force, and I don't think in your automotive catalytic converters that you would have sufficient pressure drop to give you a good separation. This is the problem also with what they refer to as direct air capture. You need a pressure driving force, and that would be difficult to put into an automotive system.
So the second question that we have is, I think it is from the previous section, the one where you showed all the facilities. So a lot of these facilities, they were huge, and I'm probably sure that they cost a lot amount of money. So is there any possibility for development recently in the developing countries like India?
No, so not that I'm aware of would be the short answer. I mean, there is some funding, particularly from the Asian Development Bank, to fund some projects, but again, you're right. The projects I'm showing you have all required significant government support to really get them off the ground. Until there is a carbon price or some form of incentive, they're not going to be cost competitive. There's no incentive to capture carbon dioxide. So at the moment, it does require government funds. I think the world is changing quite rapidly, and that situation may change. But at the moment, it would be difficult to get it off the ground unless you had that sort of funding available.
Okay. Okay. Thank you, Professor. I think we can take up the next questions after this section.
Okay. So I will move on, and I want to talk to you about a different type of membrane technology. So in gas separation membranes, it's the membrane itself that is selective, and we need to tune the chemistry of the membrane to get that selectivity. Membrane contactors are in many ways simpler. This is a picture of a membrane contactor. And in this case, the membrane acts only as a barrier between gas moving on one side and a liquid phase, a solvent moving on the other side. So this technology is very similar to solvent absorption or gas absorption, which you may have studied already in your course. So in classical solvent absorption, the CO2 would be absorbed into a solvent within a packed column. Here we essentially replace that packed column with a membrane. So the gas passes on one side of the membrane. The solvent has a high affinity for carbon dioxide, so that CO2 passes through the pores of the membrane and into the liquid. The advantage here is in terms of the scale of the equipment, and it relates a little bit to the last question that was asked. A typical gas absorption column in a full-scale carbon capture and storage process would be 22 metres high and about 5 metres in diameter. And that makes for something that is very expensive, as we just talked about. One of the advantages of going to a membrane unit is you can make something that is much, much smaller. So you can see that this would be the size of a membrane gas solvent contactor, carrying out the same performance level as the packed column. So this approach is really about minimising the size and the capital cost of the equipment, and doesn't require anything in reality other than a porous membrane. We've also looked at this, though, for membrane stripping. So you can see here the sort of membrane unit I just talked about on the left, where the gas is absorbed through the membrane and into the solvent. This creates a rich solvent, but we can pump that rich solvent into a stripper. So in this case, we then heat up that solvent, but we also operate at a much lower pressure on the gas side of the membrane, either by using low pressure steam available within the power station or applying a vacuum. And that pulls the CO2 back out of the solvent. So you can condense pure carbon dioxide and recycle the solvent. So we've been looking at both absorption and stripping using membrane contactors. The major issue here, though, is ensuring that the membrane itself remains gas-filled. If this is full of gas, this membrane, the CO2 will pass very quickly in either direction. However, if it becomes filled with solvent, if it becomes liquid-filled, then the mass transfer coefficient drops by several orders of magnitude. So you don't get that separation, the speed of separation that you would achieve if it is a gas-filled membrane. So this requires you to have a membrane that's highly hydrophobic to prevent that liquid from entering the gas phase, the membrane. Again, I showed you earlier the electrospinning work we've done. We have, in fact, here been looking at adding hydrophobicity to specifically address this issue, but still leaving us with a very porous membrane. So picture A here is a standard random electrospun support membrane, but what we've done is then added hydrophobicity either through the addition of hydrophobic nanoparticles, but also through this interesting bead on a string structure, which is again formed by electrospinning, but where we deliberately, if you like, mess up the procedure to generate these polymer beads on the nanofibre strings. I'm plotting on the right-hand side here the stripping flux or the flow through the membrane as a function of temperature. For all the membrane types, that flux increases with temperature, which is what you would expect, partly because as you increase temperature, of course, the viscosity of the liquid falls, and so your overall mass transfer coefficient also increases, but also because the thermodynamic equilibria favours the CO2 being desorbed from the solvent as you increase that temperature. But importantly, you can see here the difference between our classical asymmetric membrane, that's the one I showed you in the very first slide with a very thick, heavy support, and our electrospun support membranes. And in particular, you can see that the ones with either the nanoparticles or the bead-on string structures outperforming the standard electrospun membrane because they're able to stop penetration of the liquid into the membrane itself. But I want to move on and talk about our pilot plant trials. So I'll again just pause and ask Kriti if we've had any more questions on that section of the presentation.
So I think it might be a little related to this section. So one of the questions was, could you comment about carbon capture using nanofluids?
Well, it depends what you mean by a nanofluid. There are certainly lots of people looking at different solvents, and some of those solvents have encapsulated nanoparticles or encapsulated components that reduce the demand on the stripping column by essentially creating two phases, one that requires stripping and one that doesn't. I'm not sure if that's what was being referred to.
Okay, so I think the other question, which is sort of similar to one you talked about. So what are the characteristics of the solvent contacted to the carbon dioxide, the one which you just mentioned?
What do you mean? The characteristics of the solvent or the characteristics of the contactor?
The solvent.
The solvent, so we can use a variety of solvents. The standard solvent that is used industrially since the 1950s is monoethanolamine, and much of the projects I showed you earlier use that solvent because it's reliable. A disadvantage of that solvent, though, is that it is a little bit volatile, and so you will get some small parts per million of the solvent entering the atmosphere with the nitrogen that exits from the top of the column. The concern with that, though, is that when it hits the upper atmosphere, it can turn into a carcinogen. It can turn into what's known as a nitrosamine. And also the energy demand of that solvent is quite high. So most of the research that's going on in the laboratories internationally is looking at better solvents that reduce the energy demand. And that can be through the sort of approach we just talked about, where you have a solvent that is what they call biphasic. It splits into two phases. Or it can be things like amino acids. Again, and that new solvent development is based on both reducing the energy demand, but also reducing the environmental footprint of the solvent. Yes. That's probably enough on that. In terms of the contactor itself, you'll see in a few minutes the pictures of the types of contactors that we use.
So I think we have another question. So what is the scalability of the membrane system? But I think you are going to talk about that next.
I'll
so
show
I think
you
we'll
some
take
pictures. Yeah.
Okay. So, I'll take up the later questions. I mean, the questions later.
Okay.
The others that we have.
Yep. So if we move on to the pilot plant trials, we have had two major campaigns, or probably three, of testing these membranes at pilot scale. But as we were sort of just discussing, the more novel membranes that I've talked about today, we can't make them yet at the scale we would need for a pilot plant trial. So we tend to use commercial membrane modules in these pilot plant tests. And as you were just alluding to, we take the smallest ones of those we can get, but gas separation membranes are commercially available at very, very large scale for natural gas sweetening. So there is no problems providing the scale we need with commercial gas separation membranes right up to full scale. Membrane contactors aren't quite at that level of development, but I'll show you the size that we're using, and that's about the largest size you can currently get commercially. So they're used already commercially in some interesting applications, such as removing carbon dioxide from wine, and also in heart-lung machines. If you are having open heart surgery, your blood will be oxygenated using the equivalent of a membrane using a membrane contactor to provide that gas liquid transfer. But these are our pilot trials at a coal-fired power station in Victoria known as Hazelwood Power Station, which is actually now shut down, but anyway. And this is a picture of our pilot plant, and this is my postdoctoral fellow, who is now actually an associate professor, Colin Scholes, who was responsible for a lot of this work. And this process, we used this form of membrane. This is referred to as a hollow fibre membrane, and these we used, in this case, a commercially available module from Air Products referred to as their Prism membranes. You can see that these hollow fibre membranes are actually quite thin. They're only millimetres in diameter. You can see that by looking at the size of the ballpoint pen in the picture. And so this allows you to get many thousands of square metres of membrane area into quite small modules. If you looked at a scanning electron microscope image of one of these hollow fibres, and again, this is of the Prism fibre, you can see, though, they have the same structure as the flat sheet membrane I just showed you. So they have this quite porous open structure through the bulk of the fibre, and then it's only the skin layer on the outside surface of the membrane that provides the separation. So you can see in the module here, it operates similar to what we were talking about with the flat sheet membrane. This is shown for oxygen-nitrogen separation, which is the main application of the Air Products Prism membrane. So in that case, the air comes in, the oxygen permeates through the walls of the membrane, and the nitrogen is retained. This is our pilot plant rig shown on a different scale, and the module on the right here is that Air Products Prism membrane. So a commercial membrane module, maybe about 1 metre in length and containing significant membrane area, though, in terms of those hollow fibres. The one on the left is actually a gas liquid membrane contactor. Again, one that's available commercially, in this case full of polypropylene fibres, and again many fibres in this case, and so in this case you have the solvent flowing the outside of those fibres and the gas flowing on the inside. However, as you might expect, these membranes don't perform in the real world as they did in the laboratory, again predominantly because of the impact of the number of impurities present in the gas stream. So this is the results for the prism membrane, and we tested this membrane first in the laboratory, got a permeance in the laboratory of about 2,000 gas processing units. You can see that in the real world, the permeance dropped considerably. So about 800 when we first switched the unit on, but stabilising at around 400 to 500. So only about 25% of the performance in the laboratory. Similarly, for the selectivity, we were expecting about 20. We ended up stabilising at a selectivity of about 5. And this is not unexpected. These performance falls relate predominantly to the presence of water vapour. Again, the flue gas stream is highly saturated with water. In fact, we had many problems getting liquid water out of the pipes upstream and downstream of the membrane unit. And so because of the amount of water in the system, we see quite a significant drop in performance of the membrane. That's the gas separation membrane. This is the membrane contactor, but the data I'm showing you here is actually for another membrane contactor that we tested, which was formed from Teflon or PTFE, which we expected to therefore be very good at holding back the liquid and maintaining the membrane as gas filled. But unfortunately, that wasn't the case. You can see the performance in the laboratory given by these top two curves. You can see the mass transfer coefficient there of the order of 0.004 centimetres per second, but falling significantly in the pilot plant trials. So what was going on here? I mean, part of this was water vapour, as I've talked about, but some of the other issues also related firstly to fly ash. So the gas stream contained particulate matter, and even though we had a number of filters upstream, we still ended up with fly ash building up. So this is the entrance to that polypropylene module I showed you earlier, and you can see the fly ash building up there. So this affected both the gas separation membrane and the gas contactor. Similarly, though, in the membrane gas contactor, this is the polypropylene contactor, we also had evidence of the solvent breaking right through onto the gas side of the membrane. So that hydrophobicity just wasn't enough to hold the solvent back. And this relates a little bit just to, this relates to two things that we hadn't considered when we did the laboratory scale trials. The first thing to notice is when you're in industrial scale, the modules are no longer small, but of a considerable length. You saw in that picture, they're about typically 1 metre length, and they're operating, of course, in countercurrent flow. What that means is that you get a pressure differential not only between the gas and the liquid phase, but along the length of the membrane module. So if we step back a bit, in the laboratory, what you're aiming for is a pressure differential that is close to zero between the gas and the liquid side. If you have too high a gas pressure, the gas will bubble through the liquid side. If you have too high a liquid pressure, the liquid penetrate through the membrane and give you that membrane wetting problem that we observed. So ideally, we're aiming for a pressure differential of about 30 kPa that we know would minimise both those effects. You can see that we could get that at the solvent inlet to the membrane module, but because of the pressure drops along the length of the module in both directions, that meant that the pressure differential at the solvent outlet was much, much smaller. And this led partially to the membrane wetting effect that we saw. So again, a real effect of scaling up the process is that you're limited to the length of module you can have before this becomes an issue. You can also see that it was very hard to maintain a constant pressure differential, particularly during startup and shutdown. So this again is an issue that we hadn't quite thought through, that when you start up and you shut down, you need to maintain that pressure differential very carefully. As soon as you have a process upset, you can destabilise that pressure differential. And once the membranes are wetted, it's very difficult to go back. And it's some of these issues that really need to be overcome if membrane contactors are going to compete effectively with packed columns. However, the good news is we had much better success in a more recent pilot plant trials. So these are pilot plant trials conducted over the last couple of years at a different power station, Vales Point in New South Wales in Australia. And in this case, you can see the membrane contactor here. We only tested membrane contactors in these trials, and we used them for both absorption and stripping. But we moved to a different commercially available membrane module in this case. And this module was different in that it contained hollow fibres, but then ones that were coated with a less permeable outer layer. So the bulk of the membrane was similar to the Prism Air Products membrane I just showed you, a porous structure. But in this case, and it's hard to see in this image, there is a coating on the outside of the membrane that is non-porous. I've added some pictures there of ones we've generated in the laboratory, although the coating is a bit more clunky or cumbersome than the commercially generated ones. But you can see what I'm getting at here. You have this non-porous layer that is still CO2 selective, so it still allows carbon dioxide to pass through, but the pore size, if you like, is much, much smaller. It is of a size similar to a gas separation membrane. And having this coating on the outside surface of the membrane, if you have the solvent flowing on the outside surface, means that you can much more effectively prevent that membrane wetting. So you can see that now in the data I've got here. This again is the overall mass transfer coefficient plotted against the Reynolds number. These open circles here represent laboratory data, both some that we've produced and others from other literature studies. And you can see now that our pilot plant membrane was able to compete very effectively and give us the overall mass transfer coefficient that we required for these trials. So that's all I want to say on our pilot plant trials. Again, I'll pause for a minute to see if there's any questions. And I'll also ask Kriti how long she wants me to go for, because I've probably got another 20 minutes I could go for, or I could cut it down to 10 minutes, but let me know.
So we usually extend to like around 10 minutes after the time we have allotted. So we can extend for another 15 to 20 minutes, I think. So I will just take up a few quick questions before we move on. So one of the questions was, okay, just a minute. Yeah, so can these membranes be used for direct air capture, or is it about capturing the carbon dioxide coming out of flue gases?
The problem I alluded to before with direct air capture is that we don't have a pressure driving force. There's actually not much pressure driving force in flue gas capture either, and so we have to pull a vacuum on the other side of the membrane in order for this to work, because the flue gas pressure is only just a little bit above atmospheric. That's the same in direct air capture, but the energy required to run the vacuum pump would not be viable in direct air capture because the carbon dioxide, well, sorry, for gas separation membranes, the carbon dioxide concentration is so much lower. You know, it's 400 ppm, as I just showed you, versus 4% or 10% in a flue gas stream. So I suppose my first comment is I don't think direct air capture is ever worth doing until we shut down all the power stations, because it makes much more sense to take it from a flue gas while we've got flue gases rather than trying to take it from the air. Having said that, the membrane contactors would work in that application, in the same way that a packed column would work. And in fact, there are installations, I understand already, that use membrane contactors for removing carbon dioxide from within building air conditioning systems. So you may know that if you have a large number of people in a room, the CO2 concentration can go up from 400 ppm up towards 1,000 ppm simply because of everybody breathing. And particularly in Japan, there's been quite a lot of work done on arguing that that's bad for your health. And therefore, there are air conditioning systems now that deliberately take that carbon dioxide out of the atmosphere so that people in the room can breathe more easily. So that's a very small example of direct air capture. But I'm also, in the next section, going to show you another version of direct air capture. So I'll talk a little bit more about that.
Okay, so I think we can take up a quick question before we proceed. So I
Yeah.
think it is a little not related to the topic you have been speaking, but is it possible to capture carbon dioxide with absorption process?
Well, yes, by solvent absorption, yes, with absorption with a B. I've just talked about that. But you can also use adsorption with a D, where you're adsorbing the CO2 onto a solid. And that is a technology that is definitely being considered, predominantly through pressure swing adsorption or vacuum swing adsorption. And that's being considered for direct air capture as well as flue gas capture.
Okay, thank you, Professor. So I think we can continue.
Okay, so I will talk about something a little bit more novel that we've been working on more recently, and that this is, if you like, a form of direct air capture. So it addresses the question that was just being discussed. So I want to talk to you in this case about microalgae as a mechanism for capturing carbon dioxide from the atmosphere. If you look at the ability of microalgae to do this, you can see that it's very effective. So on the left here, I've got a graph of the tonnes of CO2 that you can capture per year per hectare by planting trees, which of course is what a lot of people think is one approach to direct air capture, if you like, is to plant a lot of trees. And you can see that you can get maybe 50 tonnes of CO2 recycled per year per hectare at the moment. And if you went through a whole heap of botany or, I don't know, some scientific studies, you might increase this to 100 tonnes of CO2. Conversely, if you grow microalgae in raceway ponds, you can capture a lot more carbon dioxide with what's referred to as Generation 3 microalgae. And with scientific technology, particularly genetic engineering, it's envisaged that we could bring that up to around 700 tonnes of CO2 per year per hectare. So this acts as a mechanism to capture carbon dioxide directly from the air, which is an abatement strategy that we've just talked about. But the algae themselves can be utilised in a number of ways. Already, algae are being used actively in water treatment processes. So in addition to capturing carbon dioxide from the atmosphere, these algae also feed off the phosphorus and nitrogen in the wastewater. And so they can act to clean up the water in a very effective manner while also capturing the carbon dioxide. The algae can be harvested then and converted into protein for animal food, and particularly for fish food, because many fish already feed off algae directly. And in particular, there's an operation already underway in Australia where we grow an algae that is particularly red in colour. And the red colour is referred to as astaxanthin. We feed that red algae containing the red dye to salmon that are grown in very large salmon farms. So salmon is a pink fish, but it's actually only pink when you farm it if you feed them on this red dye. So the fish becomes quite pink looking when you eat it at dinner, but that pink colour actually comes because of the food that's being fed to the fish. And so that's a protein that we grow specifically in Australia from microalgal ponds. And of course, the algae are full of omega-3 fatty acids, which are seen as being nutritional. To give you a feel of the price you can get, so that to show that this is quite a viable approach, that astaxanthin, the red dye I was talking to you about, ultimately you can get about somewhere between 40 to 210 US dollars, Australian dollars per kilogram of dry biomass if you were to grow that algae. Chlorella SP you can buy in our local supermarkets here as a nutraceutical or as a natural food that can increase your omega-3 fatty acid intake, and that works out at about $36 per kilogram of dry biomass. And we also in Australia grow beta-carotene, vitamin A, I think it's one of the vitamins anyway, similarly from algae. So this is quite a nice approach because you can directly capture CO2 from the atmosphere and at the same time make a profit. You may have, or you've probably heard about this approach being used to grow biofuels, and that's certainly a potential approach, but at the moment the economics aren't quite there if you just harvest it for biofuels. Where do membranes come into this picture though? And to explain this, I need to make you think about what microalgal ponds would look like. You can see that if they're going to work, they're going to have to extend for many hectares. Because until you do that, you're not going to capture a significant amount of carbon dioxide. And this is true of all direct air capture processes. So we've got to somehow get the CO2 there across these extensive ponds. And in fact, capturing the CO2 directly from the air is usually not enough. So we need to specifically add the air or add pure CO2. So to do this, we're going to need a compressor. So we can, in this case, supply either a flue gas or pure CO2 to the microalgal beds using a compressor, and send that gas into the ponds. However, because the ponds are so extensive in nature, that's going to result in a large compressor energy demand. Whether we use a flue gas, a pure CO2 or air, getting that air into those ponds consumes quite a large amount of energy. Further, we've got to distribute that CO2 in a way that it is useful to the algae. And that, at the moment, is done through injecting the gas in the form of small bubbles. That's very effective at ensuring you have a high mass transfer of CO2 or air into the algal beds. But ultimately, most of those bubbles reach the surface without fully dissolving. And so the net effect is we have high CO2 losses because a lot of what we inject into the beds simply goes back out to the atmosphere. So as I said, we can use this for direct air capture, and some of the research we're doing at the moment is focused on that. We can use air, which has this large compressor energy demand, if we're injecting it into the beds, or we could use a flue gas. But if we look at a classical carbon dioxide capture process, and I'm showing you here the standard solvent absorption process, this also is energy intensive. So you can see we have the absorber here, in which the flue gas now is absorbed into a packed column arrangement. I'm just showing the standard approach here. The loaded solvent then passes to the stripper and back to the absorber. The issue here is the very, very high energy demand of this reboiler. This consumes about between 2 and 5.5 gigajoules per tonne of CO2. And this is quite a high energy demand, as you're aware, which makes the whole cost of carbon dioxide capture currently very expensive. But the novel approach we've been looking at, and it is quite a novel approach that we're hoping to commercialise, is to actually replace that stripper with the algal bed. And I'll say that again because it's quite a difficult concept. We're replacing the stripper with the algal bed. So what happens now is we pump the loaded solvent containing the CO2 through hollow fibres which are immersed within the microalgal bed. If I blow up a picture here, you can see what I'm talking about. So the loaded solvent passes within these hollow fibres, which are identical to the hollow fibres I've already shown you, within the microalgal bed. But these are hollow fibres that have that thin, non-porous coating on the outside, which is only permeable to CO2. So the CO2 passes across the walls of the hollow fibre into the microalgae. And as the microalgae feed on the CO2, they continue to provide a driving force for that CO2 to cross the membrane. However, the rest of the charged species in the solvent can't pass through, partly because they are charged, they can't pass through this barrier. And so we end up stripping the solvent. We go from a loaded solvent to a lean solvent that can be recycled back to the absorption column. So this has tremendous advantages. We've eliminated the high energy demand of the stripping process because we have no reboiler. We also have no compressor to deliver the gas into the algal beds because the solvent itself now requires only pumping, which is a much lower energy and lower capital cost process than gas compression. We have no CO2 loss because we're not generating microbubbles or bubbles. The CO2 is crossing as a pure molecule. Sorry. And it's easier to store the carbon dioxide because it's present in a liquid form that we can easily store overnight, for example, when the microalgae do not require CO2 because they don't feed during the night. So we've been working on this for a number of years, and the work I'm going to show you, I'll try and keep it brief in the interest of time, is the work of my PhD students, Shirley and Chi, and my colleague, Associate Professor Greg Martin. You can see us growing the algae here in a small scale. So the bottles on the left-hand side here are much, much greener because we're providing that CO2. So here's our bottle of loaded solvent that we've loaded up with carbon dioxide, and that carbon dioxide enters through. You can see our hollow fibre membranes. You can just see them immersed in the liquid here. And so the solvent's moving on the inside of those hollow fibres, and the microalgae are feeding off the CO2 that comes through the fibres themselves. This one here you can see we've done as a control where we're just pumping pure water through the fibres, and so you can see that you don't get that same growth enhancement. We've tested this with 3 different solvents. So we referred earlier to the monoethanolamine being the standard solvent used in these capture processes, but we also tested an amino acid, potassium glycinate, and potassium carbonate. That's the membrane that I talked about. It's a polysulfone membrane with a PDMS outer layer. And we've tested a number of different algal species. This is a typical growth curve. You can see that we have no CO2 enhancement. We just grow it using direct air capture, if you like, capturing the carbon dioxide just from the atmosphere. We get quite slow growth. However, if we have the solvent passing on the other side of the membrane, you get this much enhancement with a partially loaded solvent and a much greater enhancement with a fully loaded solvent. So it works quite well. This is showing that the membranes don't foul very easily. There's an unused membrane on the left here, one after a trial showing some algal deposits, but after washing that membrane simply with water, we can restore the performance of the membrane. We've scaled this up into little mini raceway ponds, if you like, at a laboratory scale. So again, you can see the 2 raceway ponds on the left here without the CO2 fibres, and on the right here where we have the membrane fibres sitting on the bottom of the tank here, providing that extra CO2 through the membrane itself. However, we've gone one step further, and rather using commercial hollow fibre membranes, we move to this flat sheet membrane. This is a commercial membrane, but one which we've turned into our own pond liner. So what we've done here is overlaid 2 flat sheet membranes to form an envelope, but now the solvent, the loaded solvent, passes through the inside of that envelope and across to the outside. You can see that image on the bottom here. So the solvent passes through, and we have now effectively formed a pond liner. So this is now something that could go, if you like, as the floor of the pond, providing a lining across the whole pond that can supply CO2 to the microalgae. And this has again proved very effective. As one final step, we now also control the amount of CO2 we deliver by controlling the pH. So if you have no CO2 addition, if you've got direct air capture only, you can see the pH increasing in the medium with time because the CO2 are grabbing the carbon dioxide out of the solvent. CO2 is an acidic gas, it forms carbonic acid. So when you remove it, you get a more alkaline system. Conversely, when we're using the solvents in an uncontrolled manner, the pH was falling because we were delivering almost too much CO2. And in fact, in some of these runs here, we did see a loss of microalgae. The microalgae died, if you like, because we added too much CO2. So in our latest version of this approach, we now have pH control that controls the amount of solvent, the flow rate of solvent through the system. And you can see now we can control, maintain a quite even pH of 8 in this system. Just to finish that, you can see the effect. If we have no pH control, we supply too much CO2, and you can see that the CO2 concentration in the gas phase above the membrane is quite high. This is similar to what I was showing you with the bubbles. We're actually not being very effective because most of the CO2 we're using is actually going straight back into the atmosphere. If we control the pH with the hollow fibre membrane, we get much closer to what we'd be looking for. However, with the flat sheet liner and pH control, we can pretty much control that CO2 concentration at the atmospheric level. Air sparging also produces the same effect, whereas if we have no CO2 supply, if we're relying on direct air capture, you can see that CO2 concentration in the gas phase above the medium drops because we're pulling the CO2 directly out of the atmosphere. So I'll quickly conclude on that part, and this is my last slide, so I'd suggest you get those last few questions ready. Just to conclude on this bit, we've shown hopefully that we can grow microalgae as an effective utilisation strategy for using CO2 to generate an effective product. We can deliver the CO2 to the microalgae beds via a loaded solvent, and this eliminates the reboiler duty in flue gas capture, so significantly reducing the cost of capture from a flue gas operation. We have no compressor to deliver the CO2 or the gas to the beds. We have no CO2 loss. We have the ability to store the CO2 overnight. And the scale-up design incorporates pH control and this pond lining that we consider to be very effective. So I'm going to finish there, and I'll stop sharing my slides and open for any other questions you might have.
Thank you, Professor. I think it was a very great lecture. I really learned a lot. So we have a few questions. We actually have a lot of questions, but I'm going to take a few of them in interest of time. So one of the questions was, could you compare the efficiencies of the different processes that you talked about, like the efficiencies of the use of microalgae and the membrane process, in terms of in terms of aspects like the amount of carbon capture, or like CO2 captured, and the operating costs, that.
So first of all, any utilisation strategy, there's any strategy to use CO2, will only ever use a very, very small amount of the gas that can be captured. So I showed you in those in those large-scale demonstration projects that people were storing of the order of 1 million tonnes of CO2 per year. And they can do that effectively by storing it underground in storage, in geological storage. But utilisation in microalgae, you might, I think I showed you there, you might get 900 tonnes per year per hectare. So the largest you might have is, several thousand hectares. So you might get up to, 10,000, maybe 100,000 tonnes of CO2. You will never be able to store utilise as much CO2. But microalgae is a lot more prospective in that case than direct air capture or by turning CO2 into plastics, for instance. So any other utilisation strategy is just not going to be able to store or consume nearly as much CO2. So that the capture processes and the storage processes are much more flue gas capture, and geological storage is much more effective and efficient, if you like, in that sense. The membrane contactor versus the solvent absorption, the efficiency is identical because you're using the same solvent. The capital cost is reduced from the membrane contactor if you can get it to work. But as I said, there's still some problems in getting it to work at the scale the solvent absorption works at. The solvent absorption, you can get 95% purity and 90% of the gas capture, which is considered the normal target, but you're doing it at quite a significant cost. So I showed there, anywhere from 2.5 to 5 gigajoules per tonne of CO2. The gas separation membranes, they look like they will be able to be developed for a lower energy cost. So down at that 2 to 3 gigajoules per tonne of CO2. So not huge decrease in energy cost, but certainly at the lower end. And they'll also have a significantly lower capital cost because, again, they're quite a compact unit. But the disadvantage there is you can't get the purity of the gas. So it's very difficult to get 95% purity and to get 90% capture. So that remains the issue with the gas separation membranes. So sorry, that's a very long answer to the question.
But it was quite useful nonetheless. It was really insightful. So the other question that we have is, I think it is a little off topic. So it says that if we use electrical vehicles, so like for instance, the electric vehicles that we have in the market today, so the entire carbon dioxide generation would be transferred to electricity generation stations. So do you think they could handle the load that they will experience?
Yes, very easily, because electric vehicles are so efficient that the demand on the power station really is minimal. It's funny, I now have a fully electric car myself. I'm driving an electric car, and so I have done quite a bit of research myself on this, and they are so efficient that the demand on the power station is not that extensive. And of course, in Australia, and I would imagine in India, at the same time that you are bringing in electric cars, you're also bringing in a lot of solar panels. So I run my electric car off my solar panels that sit on my roof. And so the net demand on the power station is zero.
Thank you. Okay, that was great to know. So I think in interest of time, we would not take any further questions, but you have answered almost all of them. So it was a really insightful session, Professor. So now I would like to invite Geetika Jain, who is the overall coordinator of Azeotropy, to present the concluding note.
Thank you.
Good evening, everyone. I hope I am audible. My name is Geetika and I am overall coordinator for Azeotropy 2021. And I would like to express my gratitude and thank you, Professor Sandra, to give us such an insightful lecture on CO2 capture. I think we learned a lot and the audience must also have learned a lot from this session. So thank you very much for taking out your time and giving such a good talk. And thank you to all the audience for attending this. And we'll be uploading the recording soon on our YouTube channel. So thank you, everyone.
Thank you.
Thank you so much, Professor.